Section 14.3, Hamilton circuits and algorithms. A Hamilton circuit is a graph. A Hamilton circuit in a graph is a circuit that visits each vertex exactly once. Remember, an Euler circuit is a circuit that uses every edge of the graph exactly once. So let's think which of the circuits below are Hamilton circuits and which are Euler circuits. So looking at letter A, we start at vertex A, go to B, E, wrong way, E, D, C, F, and A. We used every vertex, so it is a Hamilton circuit. We did not use every edge, so it is not an Euler circuit. Letter B, just looking at that circuit that's written, we can see that the vertices are used more than one time. So we know it is not a Hamilton. We can check to see if it's an Euler circuit to see if we use each edge. So we go from A to B, B to C, C to D, D to E, E to F, F to C, C to E, E to B, B to F, and F to A. We did use every edge one time. Yes, it's an Euler circuit. And the last one there, B, C, D, E, F, B. Again, we can see that vertex A is not used, so it's not a Hamilton circuit. Since vertex A is not used, A to F doesn't happen and A to B doesn't happen either, so it's not an Euler circuit either. Every complete graph with 3 or more vertices has a Hamilton circuit. Remember, a Hamilton circuit is a circuit in a graph that visits each vertex exactly once. Hamilton circuits that differ only in their starting point are thought of as the same circuit. So the circuit could be BCA is the same circuit as circuit CAB. Example 2, draw a complete graph and count the number of Hamilton circuits. If there are 3 vertices, here we go. A, B, and C are our vertices. To find our different circuits we could possibly have, we'll start at A. And from A, we could either go to B or C. If we went from A to B, then we have to go to C. If we go from A to C, then we have to go to B. Did something wrong. No, I didn't. We've got circuit A, B, C, and circuits A, C, B. There are 2 Hamilton circuits. If we talk about 4 vertices, draw it. There we go. So we can start at vertex A. And from A, we're going to B, C, or D. If we go from A to B, then we have to go from C to D, C or D. If we go A, B, D, we have to go to C. If we go A, B, C, we have to go to D. If we go from A to C, then we can go to B or D. If we go A, C, B, we then go to D. A, C, D, we then go to B. If we go from A to D, we then can go from B or C. If we go A, D, B, we then have to go C. A, D, C, we then have to go B. And to complete the circuit in each case, we have to go back to A. There are 1, 2, 3, 4, 5, 6 Hamilton circuits for 4 vertices. If there are 5 vertices, go ahead and draw it. We've got A, B, C, D, and E. And make it the complete graph. So if we start at A, we can go to B, C, D, or E. If we went from A to B, we could then go to C, D, or E. If we went A, B, C, we could then go D, E. A, B, D, we could then go C to E. Or A, B, E, we could go C or D. The letter not used is E. The vertex not used, I should say, is D. A, B, D, C, E. A, B, D, E, C. A, B, E, C, D. Or A, B, E, D, C. Okay, this gives us 6, and then each time we have to go back to A to complete the circuit. This gives us 6 circuits from branch B. There will also be 6 from branch C, 6 from branch D, and 6 from branch E, for a total of 24 Hamilton circuits if there are 5 vertices. The number of Hamilton circuits in a complete graph with n vertices is n minus 1 factorial. In a weighted graph, a minimum Hamilton circuit is a Hamilton circuit with the least possible total weight. We've got the brute force algorithm for finding a minimum Hamilton circuit. Choose a starting point, list all Hamilton circuits with that starting point, find the weight of each circuit, and choose a Hamilton circuit with the least total weight. Example 3 says use the brute force algorithm to find a minimum Hamilton circuit for the graph below. Right? We've got a weighted graph. We've got the numbers. We've got 4 vertices. And if you look back to example 2, we already wrote all the Hamilton circuits that go along with it. So I'm just going to rewrite those Hamilton circuits, A to B to C to D to A to B to D to C to A to C to B to D to A to C to D to B to A to D to B to C to A, and A to D to C to B to A. Okay, now we need to add up the totals. So A to B is 3, B to C is 6, C to D is 3, D to A is 1, for a total of 13. A to B is 3, B to D is 4, D to C is 3, C to A is 1, for a total of 11. A to C is 1, plus C to B, which is 6. B to D is 4. D to A is 1, a total of 12. A to C is 1, plus C to D is 3. D to B is 4. B to A is 3. Our total is 11. A to D is 1. D to B is 4. B to C is 6. C to A is 1. Totals 12. A to D is 1. D to C is 3. C to B is 6. And B to A is 3, for a total of 13. The minimum Hamilton circuits are these ones that total 11. So it's AB, DCA, or ACDBA. The brute force algorithm is inefficient because it requires us to calculate the total weight for each of the n-1 factorial Hamilton circuits. So even thinking back to example number 2, when we had 5 vertices, we were going to have to calculate 24 weights for those different Hamilton circuits. No efficient algorithm for finding a minimum Hamilton circuit is known, but an algorithm that gives reasonably good solutions most of the time is the nearest neighbor algorithm.